In this lecture, we'll study rank 1 matrices and structure tensors. See the definition. A rank 1 matrix is a matrix with rank equal to 1. Here we have an outer product representation for rank 1 matrices. Every rank 1 matrix A in n by n dimensions can be written as an outer product. U V transpose, U is from Rm and V is from Rn. For such rank 1 matrices, we have this norm estimation. A metric 2 norm is the same as a metric Frobenius norm, and that is also the same as the product of two norms of U and V. We can prove it quite easily. Metric 2 norm of A is defined in this way or this way. So we try to get maximum of AX with the condition X2 norm is 1. Now for this portion, here A is UV transpose, so that we can get this one. Now this one is a scalar, so the scalar can go out and remainder part is U2 norm. Now we have to maximize over the X norm is 1, but this dot product is the same as, this dot product is the same as V2 norm times X2 norm and times cosine theta. Theta is the angle between V and X. Now this value is 1, and then now it is maximized when cosine theta is 1, so that this portion is the same as with maximum, same as V2 norm. So we have this result. For Frobenius norm, you can prove quite similarly. Let's see this one here. Now U and V are given, then let's try to form A explicitly. Now U V transpose is same as here. U is a vertical vector, 6, 3, minus X, and V transpose is a row vector, which is 1, minus 2, and 2. Now this product can be obtained in this way: row, column, which is 6, and first row, second column, that's minus 12, and third column, and 12. From second row, is 1 and 3, and 3, 1, and 3 minus 2 multiplication is minus 6, and 32 multiplication is 6. And for last one, now first row, minus 6, and that is 12 and minus 12. Right? So that is explicit construction of U V transpose. Now it is asking to find a 2 norm, which must be same as U2 norm, and times V2 norm, right? So let's try to get U2 norm, which is same as now square sum and square root. So that is 36 and 9 plus 36. That is 72 plus 9. That's 81. So it is 9. Okay, how about V2 norm? That is now square root of 1 plus 4 plus 4, which is 9. So that is 3. So here we can conclude a 2 norm is this product, which is 27, right? Okay, now we'll go to structured tensor. Structured tensor is a metric, and in the form of rank 1 metric, like this one, gradient for given function, gradient and gradient transpose. Let's see definition. The structured tensor is a metric derived from the gradient of a metric, gradient of a function f, defined on Rn, and now it is defined in this way, and that describes the distribution of the gradient of f in a neighborhood of the point x. The structured tensor is often used in image processing and computer vision. Let's see this claim. Structured tensor in 2 variables, and because image is defined in plane, so let's consider a function in 2 variables. So x is now xy in R2. Then the structured tensor in this form, definition, can be written explicitly in this way. Now that one is f sub x, f sub y, vertical vector, and this one is now row vector, f sub x and f sub y, so that this outer product will make this one. As you can see easily, the metric is symmetric, and because of this structure, this is positive semi-definite. That means that the eigenvalues are non-negative. Okay. Now, the 2 norm of S is, from here we can easily see this one, gradient of f, 2 norm squared. Now that is the maximum eigenvalue. This metric has 2 eigenvalues, and maximum one is this one. We can check it easily, and the corresponding eigenvector is the gradient itself. Okay, here let's check that, and S times gradient of f. Okay, start with this one. Then S itself is now gradient f and gradient of f transpose, and we multiply gradient of f. Then this portion is the same as gradient of f norm squared, right? So that is gradient of f norm squared, of course, 2 norm, and gradient of f. So the metric times a vector is same as a scalar times the same vector. That means gradient f is an eigenvector corresponding to this eigenvalue. So that is the large eigenvalue, and the corresponding eigenvector is gradient of f, right? Now, from this one, we can check the determinant, okay, AD minus BC. Then you can easily check that the determinant is 0. Determinant of a metric is the same as the product of eigenvalues. So the other eigenvalue must be 0. Okay, so here we can get eigenvalues and eigenvectors. Larger eigenvalue is the gradient of f norm squared, and the eigenvector is gradient of f. And for the smaller one, 0 eigenvalue, you can easily check that this one is the eigenvector. We have some official proof, but already we proved over there. Now we'll try to apply the structure tensor for color image processing. Then color image I has three components: RGB, red, green, blue. Okay, for that one, now we can get a gradient that is for the three components x derivative, y derivative. Now we can formulate the structure tensor of I. So we use S sub I. That is here gradient of I and gradient I transpose. Okay, that is gradient of I and that is transpose. And with this computation, it becomes dot product of these vectors. So we have this one and these four components for that structure tensor. Now, exactly the same way, we can find the eigenvalue of the structure tensor. Now, that is the S sub I 2 norm, which is the same as this 2 norm squared, and that will be the large eigenvalue of the matrix. Now, to find the eigenvalue explicitly, and we start with this name. We try to give the name that is for JXX, JXY, the same, JXY, and that is JYY. So it is a kind of a Jacobian. Now, from this one, now we can get S sub I minus lambda I and try to get determinant equals 0. The characteristic equation, and that will be a quadratic polynomial. And by using quadratic formula, we can get such a solution. Larger one is this one. And by using a little bit of algebra, and we can get that one. So large eigenvalue, lambda 1, is given in this way. If you choose this one, negation, negative, minus, then that is a smaller one. Okay. Now, in practice, and large ones are only used so that we'll try to use that one, and then the corresponding eigenvector must be this one. But this eigenvector is directing the at the normal direction, so that when we try to work on, for instance, edge detection from color images, then we can use this color version structure tensor to get the magnitude. But now magnitude must be here square root of large eigenvalue. After getting this one, take a square root to produce the gradient magnitude, and that will give the edge normal direction. So that after getting this quantity, you can thin the edges, and finally you can decide the useful edges in edge detection. Okay. Now, structure tensor can be implemented quite simply. Okay, here we have U notation. U is a color image. Now, after getting Sobel derivatives, just the x direction, y direction, and by using that, here that is now dot product in third direction. So there's a JXX, exactly the same notation as in this derivation. Okay. Now UX, UY, third direction dot product, and JYY is UX, UI, now third direction dot product. Okay, we have here discriminant, okay, after taking square root, again, is this saved in D, and the large eigenvalue is made in this way. Look at here the mathematical formula. That is saved in D, point for each point, and then now we get the large eigenvalue, and its square root is now the gradient magnitude, and V1 is this one, so that y component and x component are used to get the direction angle, and by using the function tan 2, and that is now the h normal direction. Okay, and of course the value of theta will between here, that is minus pi to pi. Maybe one of them is exclusive. Okay. Now, how about Sobel derivatives? Okay, for image, once it comes, then now if it is not in double precision, then we change it into double, and here we define the kernel, and that is for the vertical, the convolution, the Sobel derivative, and it is used for now vertical derivative. We say in this case that one x derivative, and by using valued option in the function conv2, and we try to get one grid, the small size of the output, and it is saved for only interior points. And then now we try to expand up to the boundary by copying the near round boundary. So we can expand that. And here you may try to use the same option. Then you may get the output of same size. However, the built-in function convolution 2 has some boundary effects. So you have to be very careful. If you try to use it without care around the boundary, then you may get a really wrong answer. Be careful when you are using the filters and it's touching boundary, then you have to be really careful. The reason is that once two arrays are now overlapping only partially, then the built-in function conv2 is try to expand the values with 0. That's called zero padding. But the zero padding is, in fact, the abrupt change of function values, so that out of that, if you try to get the convolve the values, then it may be useless. So that, like this one, only try to get valued values, so it is a very correct value. And now from there on, you may try to finish the boundary values either by expanding, or and you may try to compute the same manner along the boundary, and you can fill out the values around the boundary. But here we simply just copy from inside last second row and columns, and we copy the quantities to fill out the boundary lines. Okay, that's it. Thank you.